Okay, now let's take a look at our next coding exercise on quadratic programming. You can find this notebook by clicking on the third notebook here, Quadratic Programming, and you should see something like this. And this notebook will basically follow similar procedure as before, but this time tackling a quadratic programming problem. We'll first inspect the problem and then solve it using Scipy's optimize.minimize function. Then we'll analyze the results as well. So first, inspecting the problem, let's consider this following QP problem where we're trying to minimize f equals x1 squared plus 3x2 squared. And we also have two inequality constraints here. They are linear, so that's why it qualifies as a QP with the quadratic terms in the objective function. Now, to begin, we'll visualize this problem in 2D. But if you remember, before we can create plots using Plotly, we first need to define our xy ranges and then subsequently the objective function and the constraint function. So take a few seconds and try to do it here. You can create a new code block or you can try and think about how to do it. And later on, you can then click the Show It button here as well. Okay, now let's click Show It to see how we've done it here. It's basically very similar to what we've done before. We define x1 and x2 and then use it to write out our objective and constraint functions. And once we've got these variables defined, we can now move on to visualizing the objective as contours and the constraints as regions. So we first create a figure, define the layout, and then create a contour plot for our objective function. Then in here, we'll create the contour plots as well for constraints, but specifying its type as a constraint and the operation correspondingly. Then once you run this code block, you should see something like this. Here we have the objective contours in the background and two linear shaded regions. We know it's linear because they are straight lines. The contours as well, you can actually see that this is a quadratic contour because it is curved in such a way. And compare it to our previous example when we have contour lines that are all straight lines just tilted to another direction. So that would be what a linear contour looks like. Here we have a quadratic contours characterized by its curvy shaped contour lines. So here again, we have some questions that you can have a think about and later use your notes to answer in the quiz. So now we can visualize the problem in 3D. If you remember from before, for the objective function, when we visualize it in 3D, it becomes a surface. If you extend this thinking to our constraint, because the constraint is also just a function in our two-dimensional design variables, they are actually surfaces as well. But it won't actually provide us with a lot of information if we plot them as surface. So what we want to do is that we want to just plot the invisible region because those are the area we want to shade it to express that it is invisible. So we want to find out those invisible areas and then project it onto our objective surface to highlight the invisible regions over there. So to do that, first we need to create the figure that is a 3D layout. And here we're going to create the surfaces for our constraints. We first create a mask to extract all of the values of the constraint where it's greater than 0. So these are the points where it doesn't satisfy the constraint. So these are the invisible region. And then we'll create an empty array for the surface that has the same structure as our objective function with the default NaN value. And what we're doing here in this line, set mask equals f mask, it means that we want set to be just like the objective value. So if we plot it, it will become just another objective surface. But we want to mask it so that we're only plotting the points where they are invisible. So when we do this, we basically extract all of the points on the objective surface where we want to shade it as gray. So once we've got this array, we can plot it just like our objective surface. And we change the color scale to just one gray color. And then we can also change the opacity as well. Then once we plot it, you should end up with something like this. So we have the original surface that looks like a slightly curved function surface. And then we have two colored region on this particular surface. these are the points on the surface where G will be greater than 0, meaning that the constraint will be violated. So this is how we can plot or visualize constraints on a 3D as well. Now, feel free to try out these questions and see if you can answer them in the quiz. Now we can use Scipy to optimize this function. The Scipy function we're going to use is scipy.optimize.minimize, and this method has such a signature. It takes the objective as a Python function, so we need to wrap our objective definition into a Python function. It might sometimes need some initial points, the constraints, and also the bounds for the objective space as well. So have a try in writing out the arguments, and then we'll click the Show It button to review the answers later. Okay, so see if you've got it. In here we have the objective function. We just name it func as our objective function. We also want to extract x1 and x2 from the X array here because this conforms to Scipy's format. It's going to take only one input, which is x, which would be a numpy array or a set or a tuple, but it essentially combines all of the x elements in your x design variable vector. And we want to return the objective value, which is x1 squared plus 3x2 squared. Then we can do the same thing as before, define the left-hand side of our inequality constraints, and then define the lower bounds for our inequality constraints as well. And note that Scipy uses the form ax greater than or equal to lower bound. So it's the reverse version of what we're normally used to, smaller than or equal to 0. And then you can define the upper bounds for inequality constraints. In here, they are infinite. And then we can assemble this linear constraint using a linear constraint class provided by Scipy. And it takes the A, the left-hand side of the inequality constraint, the matrix, and LB, which is the vector for the lower bounds, and then UB, which is the vector for the upper bounds. And then we can also define the bounds for the objective function. Now, if you don't know what values to use for the bounds, you can simply choose something very generic like negative infinity to positive infinity. Or if you go back to our plot, you can actually see that this plot in the design space that we care for, at least, has a lower bound of around 0, and then it goes up to some other values. So we can say intuitively that the bounds would be 0 to infinity. And then we can supply all of it into our QP, into this function, minimize, and put func as our objective function, x0 being our initial guess, and then constraints, linear constraints, we need to put a list into it because you can have more than one constraints, and then the bounds for our objective function. And once we run it and then show the results, you should see something like this: optimization terminated successfully, the function value of the optimal point itself, etc., etc. So now we have the optimization successfully being run, we can plot the results. So here, similar to before, we will use result.x to extract the optimal point's coordinates, and then we can create a figure, add the traces reusing our contour object and the constraints objects, and then plot the minimum over there using result.x, indexing it at the 0th location and the 1st location. And you can see this is where our optimum point actually is. And there's one active constraint and there's one inactive constraint. So we can also visualize this on the 3D plot and see what it would look like. In here, to plot the minimum in 3D, not only do we need the xy coordinates, but we also need the z coordinate, which is the function value. So we can extract it using result.func to extract the function value. And you should see something in here like this. If you zoom in a little bit, you can see that indeed this is where the lowest possible location of the contour, because we can't go into the gray area. So it has to be this point over there that is still within the feasible region and is also at the point of the surface here. So this is how you can make sense of the solution of your optimization result just by plotting it out, asking yourself intuitively using this kind of geometric intuitions to help you and guide you into understanding whether your implementation was correct. And that's the end for convex optimization.